Okay. So today we're on our second day of stacks. And the good part is we're not really learning the stack because we have the stack. We have push, we have pop. We looked at a way to do the stack. You know, how do you want to handle the count? How do you want to handle one thing after another? If I threw out a quick pop quiz, which I can do on here, but I didn't, if I'd say array, push goes where?
At the end.
The
At
end.
the end. And pop
Also at the end.
at the end. Right. They're the same when it comes to stacks. And if I said a linked list, we pushed at,
The beginning.
yeah, and we popped from the beginning. And it's that whole last one in is first one out. So they really have to match to follow that. Last one in, first one out. And again, on Wednesday, we're going to do something called a queue. How do we do that? It's going to be similar to a stack. So we'll do that Wednesday and Monday. And then our first test will be next Wednesday. Okay. Finally get to score some points and do well. So today we are, and I'm going to switch over, going to work with stacks. I do one or two CPS 230 once in a while, and I get into a bunch of stuff that I call selected topics, and it's extras. And one of the big one is I think you folks should be quick numerically with base 2, base 10, base 16. And we do a whole bunch of work in that class. I don't see 230 on my schedule in the spring yet, so I don't know if I would have that or not. But one of the things I may ask the student to do is A94B CF10. These are base 16 numbers. And could you add those? Could you think a little bit outside the box and work with what's called hexadecimal? Well, one of the two things we're going to do today, we're going to do a little bit of conversion, how a program is written that we're going to take a look at. We don't have to create it, but I want to quickly be able to convert a number from base 10 to base 2. Base 2 is binary. It's binary digits, it's zeros and ones. So I'm going to have this base 10 number, and we're going to use 23, and it's in base 10. And what does that equal? I don't know how many digits it is, but I know it's going to be several digits. What does that look like in base 2? Now, some of you take discrete structures and you do some work with that. But I think it's a relevant topic in our CPS 230 class that's not really covered that well. Just like the second thing we do is called this whole work with infix, prefix, and postfix. In my CPS 230, I had a whole bunch of, we spent time actually doing that. It's incorporated into the class. So today I want to start with, let's get the math before we start writing the program. We may have to draw a picture here and so forth, but what would a program look like to convert base 10 to base 2? And the way to do it, as you're going to see, is we're going to use a stack. We're going to use a stack. So down here, I'm going to start with, okay, I should do this in pencil so I don't screw it up. I'm going to divide that 2 into 23. There's lots of different ways to do this, but this is going to make for a nice program that ties right into what we're talking about. 2 goes into 23 how many times?
11, remainder 1.
11, and the remainder of 1. I'm going to write it over there. 2 goes into 11 how many times?
5, remainder 1.
5, with again a remainder of 1. And look what I'm doing. I'm putting a bunch of ones, stacking them one right on top of another. 2 goes into 5.
2, remainder 1.
2 times the remainder of 1. 2 goes into 2.
1, no remainder.
1 time with no remainder. And 2 goes into 1.
0, remainder 1.
0 times the remainder of 1. Okay. Wow. I think I see my stack already. I kept stacking the remainders up. I'm thinking of this coding wise. Wait a minute. I'm going to keep going in a loop. I'm going to keep dividing until when? When did I know to stop?
So the number could no longer be divided.
Yeah, when this became 0. When this became 0. So, oh man, I need to go back to get to those divisor, dividend, the dividend, whatever they are. If I mathematically knew the names of them. How do I show the answer? Pop and print. 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 I just did 23 in base 10 to 10111 in base 2. Some of you may know this is the 2 to the 0 column, 2 to the first, 2 to the second, 2 to the third, and 2 to the fourth. And this is a 2 to the fourth. What is 2 to the fourth?
16.
16. 2 to the third is, but there is no 2 to the third. There is no 8. 2 squared is a 4. 2 to the first power is a 2. 2 to the 0 power is a 1. So I have a 1, a 2, a 4, and a 16. Shabuzi, 23. So this is just a way I know to go through and, this is 3 times 10 to the 0 power plus 2 times 10 to the first power, etc., etc. So I just was able to do the conversions. Could I write some pseudocode here? Could I have a loop until whatever I want to call this is 0? While, what do we want to call that?
Num.
Num, good. While num is not equal to 0, what am I doing inside of here? I
Isn't it
needed
like
to,
num mod 2?
num mod 2.
Is that it? I don't know.
Okay, so what am I doing with num mod 2?
Getting the remainder
And where am I putting that remainder?
Into a
in.
stack.
Yeah, so could I even just do this? Push num mod 2. That pushes the 1 on my stack. Now what would I do?
You would need to divide num by 2 as well.
Num equals num integer division 2. That would give me a new number. You mean that's kind of it? Yep.
I have a question. Would you have to move num equals num divided by 2 before push or no?
So let's run through it in our head. If I have 23 is my num, okay? And if I do this first, num int division 2, so this is my variable num. If I do this first, this is a great question, by the way. If I do this first, this gives me what number?
11.
11. If I do this second, I'm getting the remainder from 11. I just lost this first one.
Oh, I see. Okay.
So the order is absolute great question. I just did it. I led you into these questions because I knew what to do, but that's a great question. Now, what would I do? Well, it looks like I'd do this part and then I would start. How many numbers do I have to pop?
No, we don't exactly know, right?
We don't. Could we?
Um,
Set up a counter.
Why not have count plus plus in here?
oh
Keep
yeah.
track of how many there were. Yeah, now I'm thinking a for loop, one to count. Pop. And again, we said this is going to be a reference variable. So pop REM, display REM. That's not so bad. Now go to D2L. You are going to see something that I posted for today. And I don't know where I put it. Somebody pull it up and share it. That would be great. It's called Code Samples, Chapter 7, because this is in the NIOP book. This is the NIOP, thank you. This is the NIOP book, Chapter 7. So if I look inside of that 7.2 conversion from base 10 to 2, get a number. Oh, while number equals that, then we push it onto our stack. Then we did that in. So they did the remainder first and pushed it, but they didn't change the number. So yeah, we may have been able to. I think I was wrong when I said that order mattered because we were pushing the remainder, but we didn't change number. So I need to erase that out of my notes because that was wrong. Whoever brought that up, you were right. Was that you, Logan? Yeah, my bad, my mistake. Yes, so they find the remainder. We just put it all in one line. And then, oh, while not stack of remainders dot empty. Well, there's a function. So again, go back to CPS 121 and I would get three programs exactly alike. Come on, people. I know you're cheating. It's easy. Now that you know there's a million different ways to do something, and you got all kind of stuff going on in there that when students are cheating or not. Okay, so let's see. This uses stack.h. It has an include for it. So down below, they have NIOF's version of stack.h. Now we're going to be getting code samples from NIOF throughout the course, and all of these are pretty much cut and paste. So we have stack. So if you kept scrolling down, thank you, Jack, you see we have all stack, and there's a demo file, and we just have a bunch of files he's offering. What did we call it? We called it int stack and dine int stack. Is that what it was for Gaddis? But you can use those. You can use these. They all have the same empty, push, pop, display. Several, the functions are all the same. Okay, so sometimes you grab what you want. I want you to take a couple minutes on your own, and I'm going to pause the recording so somebody remind me later. I want you to cut and paste and get that base conversion working. So you have it. Get it out of there. You can use so really, it's wide open what you can use. You may have to change a line or two of code depending on which stack class you use. You can use the arrays. It's up to you. You can just go what they ask for. That's fine. So now that we're getting this to work, I want to know, my question is, will it work with a different base? So let's take a number. Let's take 100 and let's convert that to base. Somebody give me a number.
8.
8. We want to convert this to base 8. All right. So I'm going to put an 8 here. And I'm going to do the work here on this end. Let's see. If I go to my base 8s, and this is another way to do it. This is 8 squared, 8 to the first, 8 to the 0 power. That's the same as 1. That's the same as 8. That's the same as 64. I need a 64. That leaves me with 36. I'm going to need 4 8s. That leaves me 32 with 4. And I'm going to, so it should be 144. Now, do I expect you to know what I just did? No, but that's another way that we can convert.
It
In,
works.
in my, okay, good. If I take 8 into this, it goes 1, that's 80 and 22 with the remainder of 4. 8 goes into 12 one time with a remainder of 4. 8 goes into 1 0 time with the remainder of 1. There's my pop 1, pop 4, pop 4, and it does in fact work. So this is kind of nice. And again, some of you have to take discrete, well, probably most of you, if not all of you. And when you get ready to do conversions, if you remember this, you're going, bam, and knock that bugger out in no time.
Is that a math class?
Discrete math, yes.
Yes.
Okay, well then, yes.
There's after the calcs, it's discrete and diffie-q, differential equations. That's all part of the AS program for your associates. Okay, I think that's kind of a cool program. I think this is kind of cool usage of our new data structure stack. So this is the way this course is just going to keep going. We're going to learn about a data structure and we're going to say, well, how in the heck is this relevant to anything that I might want to do? Well, here's one example. Flipping the page. Here comes another example. If any of you had me for 230, which I don't know, you would have known we talked about infix, prefix, and postfix. And the notion of how this works is actually pretty cool. And this is an introductory to some of the stuff we're going to be doing later this semester. We're going to be doing a lot of work with trees. And I'll throw some terms out now as we go. But what is infix? Infix says the operator is going to be between the two terms, between the two expressions, but the operator is going to be something like A plus B. The operator is between these two things. So it's all about the operator. Prefix, the operator comes first. Postfix, the operator is last. The operator is last. Okay. Let's just practice that idea real quick. If I gave you this expression, A times B plus C, what operator gets done first?
Multiplication.
The multiplication. So this gets done first, this gets done second. And what you're going to see is I'm going to write it as, well, this, and I'm doing it in pencil. This whole thing gets done first. Once I have a result for this whole thing, I now just treat it as a single thing. So now I have this single thing, C plus, and this is called postfix. This is called postfix.
Quick question.
Yep.
I know we're not there quite yet, but like I know that infix is like a lot slower when doing a lot of numbers with like C++, is the difference in speed between like prefix and postfix noticeable, or is it the same kind of deal that like the it can be parsed at the same speed?
Should be at the same speed.
Okay.
And again, that's that thing called big O notation. And that's a project of ours we'll have coming up. What do you think this might be in prefix?
Multiply plus ABC.
Okay. So multiply plus A, B, C. So by way of what you said, this would be A plus B, and then that becomes its own thing times C. No, that's not what I want to do.
Oh, okay. I
Should
had it.
be,
I'm going to do, and somebody else have it?
yeah, multiply AB and then plus C.
Nope, not yet. Oh, I saw him. No, not yet.
Plus sign, multiply sign, A, B, C.
I'll take that.
Yeah, I had it backwards.
Here we go. This gets done first, A times B, and then it gets added to that. So the operator term, operator. So that would in fact be prefix. Oh, okay. And again, this created a whole term. Well, let's switch it up just a little bit. This time I want to do A times B plus C because the parentheses have some say.
For postfix, would it be BC plus?
Okay? I'm gonna start out with a hint. The A, B, C will always be in order. A, B, C, A, B, C, A, B, C. So it's going to be A, B, C. The only thing we're doing is moving the operators. Well, let's see. I'm going to do this to make it a term. B, C plus. Now I have A times term. So it's going to be A, the first term, the second term, and then multiply. Prefix, I'm going to do this first, times BC, then it's term times A plus BC. Again, ABC, ABC. How about one more, but I make it really hard or harder? A plus B times C slash D minus E. Just do postfix. Just do postfix.
Is that a times or a plus in the middle of B
Times.
and C? Okay.
Let's see. This would get done first. This would get done second, third, and fourth. AB plus. I got DE minus. Now it's going to be this, that, and slash. And then this term and this term are multiplied together. AB plus CDE minus slash divide. So the DE and minus go together. The C divided by DE minus goes together. This first term times the last term. Ooh. Okay, just coming back up here for a little bit. Infix. What does infix look like? Well, I said these become these things called expression trees. And an expression tree for infix is going to look like this. Here's the plus, here's the A, and here's the B. Okay? These guys are called nodes. The nodes are connected by edges. We're going to talk about how, like, the upper level, what's in this top node, in this case is plus, is a parent to A and B. A and B are children or child nodes. So all of this is gonna go in the future. So I'm gonna ask you a quick question, and I'm gonna put some labels in that this is my node up top, this is to the left, and this is to the right. Okay? So if I start out with infix, infix is gonna go, not ifix. That's like IHOP. Now you know why I did it in pencil. Oh my God, I almost started to write IHOP. Infix is going to be what we see here. That's the A plus B. So that's going to be left node right. It's A plus B. Now, what would prefix be?
Node left, right.
Yep, node left, right. Again, you notice the left and right didn't change order. It's only those operators that move around. And finally, postfix is going to be
Left, right node.
left, right node. This is huge building blocks for something we're going to do later in class. Lots of stuff with this prefix, postfix, and infix. Now, we got this nice postfix problem. Right here it is. This is great. But what if I would have had something that looks like this? 4 plus 2 times, where I'm actually putting in single digit numbers, times 8 divided by 6 minus 4. While we're here, what is the correct answer?
24.
I hear 24. That's the math nerd in a lot of us. We see a problem, like, gotta solve it. It's 24. In case anybody else cares. Anybody in this group? Nobody cares? Okay, but I do know the answer. Yep. You know exactly what I'm talking about. Okay. And if I went through and made this into a postfix expression, what would it look like? Oh, no, wait a minute. We said that one was going to go first. So there's a 6, 4 minus. And then we had 8, and that's 6, 4 minus with a slash. We had the 4, 2 plus, and we had the multiply on the end. Postfix, nice. So the question is, why am I telling you all of this today? Why am I telling you all this today? Well, follow along with me. Push 4 push, 2. Operator, add. Pop, pop. Pop, pop. Pop, pop now gives me what value?
6.
6. So I push the answer. Push 8. Push 6. Push 4. Operator, pop the 4. Oh, the operator's a minus. I need to make sure that that 4 goes on what side? The right side of the minus. So as I'm popping this, the plus and multiplier are not bad, but minus and divide I have to be careful with. So when I subtract 4 from 6, I just pop the 4, I pop the 6, I subtract them, and what do I get?
2.
2. Uh-oh, I hit multiply, right? I had to remember to do 6 minus 4. I got the 2. Now, now I divide. So I'm going to pop the 2. It's got to go on the right. I'm going to pop the 8. So I pop the 2, I pop the 8. I get an answer of
4.
4. So now I'm going to do the 4 in here. 4. So now what? I hit multiply. 4 to the right. 6 to the left. And I get 24. What did I eliminate from my original infix expression to this postfix expression? What is gone?
Parentheses.
Yeah, the parentheses are gone. So if I had a program that could convert this guy into postfix, I can solve that expression using pushes and pops of a stack to get the answer of 24. What do you think about that?
I have a question.
Yep.
How would you like, so say for example, 8 divided by 2, we got that 2 up there. How
Yep.
would you know to go back down that like stack to the 8? Like how would you type that out?
So
Sort of.
just remember, these are gone. So when you go and you hit the operator, the divide, you're doing pop, which had a 2 in it. Then you're doing a pop, which was this 8 that was in it. So right now, all this stuff we have crossed out, the only thing that's really in the stack is a 4 and a 6. So when I hit that last multiply, I do a pop, it's just the 4. I do a pop, it's just the 6. And that gives me my final answer, 24.
So basically, every time you do any math with anything, you push it out of the stack once you no longer need it.
When you have an operator, yeah, exactly. Remember, if this is a linked list, we keep inserting at the beginning and destroying nodes. They're out laying around in memory. We don't need them anymore. We're done with them. Well, so my stack class again being written and pushes and pops. Here's an application of, could you write a program to solve this? No. Could you write a program maybe to convert it to this? Maybe, etc., etc., etc. Okay. Do you want to do advanced level one time? Do you want to do something a little bit advanced one time?
Yes.
Yes.
Sure. Okay. So I'm going to give you an expression. Let's see what I got. Just going to make something up. And I'm going to do 2x minus 11 divided by 4 times 3. Y. Oh boy. If x and y were real numbers, what would you do first?
multiply them against the coefficient.
Yeah, you probably would do this guy first. So you would have a node like 2, and you would have an x, and you would multiply those. Now, the next thing would be the minus 11. Well, you have this is your left side, and this is your right side. So we would go up and say, there's my left subtree. Here's my right, where it's just a child node. Then this whole thing gets divided by 4. Over here, I have a times 3y, and then that whole thing gets multiplied. So there is, and this is called a binary tree because we have a left side and a right side. There is a binary tree for this expression. We wrote it out. It's kind of cool. Now, why did we do that? Well, remember when I did a little bit of this over here, and I said infix is left node right. Infix is left node right. So I'm going to take a look at this bad guy, and I'm going to go all the way to the left, which takes me down to the 2. Then I go back to its node, times, then to its right, x. Now this whole thing became a left. Here's its node. Remember, we're doing left node right. There's minus, and then here's its right. This whole thing now became a left. This whole thing became the left. Here's divided by, which is the node, and here's the right. So doing this, what's called an infix traversal, I get my original equation. I go up, this whole thing becomes the left. Here's the node, and now I go to the right. Oh, but I can't do it yet because it has a left. So I need to do this left node right 3 times y. Then I go back and do and have that times. Ah, okay. Shall we make it hard? Pick one, prefix or postfix?
Post.
Postfix. And in my postfix, it's left, right, node. Let us give it a try first. Okay. And again, I'm doing this in pencil.
Will you do it in prefix too, just so we can verify that we know?
Sure. Prefix, that means the node is in the beginning. Okay, so the node is first, so that's times. Then I go to the left. The node is first, that's divided by. Go to the left, that's minus. Go to the left, that's times. Two, x. You notice how that became a thing. So I do node left right times 2x. Then I do node, which is my left over here. There's my right, which is the 11, and then the minus. Then I have all of that. Here's my left, here's my right, here's my node. And then on this side, it's going to be node left right times 3y. And then it's this whole thing times that thing.
So in situations like these, it would be best to make the tree first, correct?
Yes? You mean draw the picture?
Uh,
Okay.
yeah.
Yeah, draw the picture. You eventually can get good at some of these. Like I've done them enough that I could do these probably without looking at a tree. Yeah. Oh, and the stuff we're going to learn based on trees and how we work with these, it's just and how we fill them. But we're going to see this left, right node, these prefix, postfix, and infixes quite a bit down the stretch. Now, what is it I needed you to get? I needed you to get the postfix, get the idea of how that postfix works. Because for today, you saw in this previous example that this postfix, I can use a stack and solve it. So for the rest of class, Jack, can you solve, or excuse me, can you share the PDF again of that code? Scroll down to the bottom. Not the bottom, the last batch of code. Keep going, keep going, keep going. This is wonderful, good. Oh, and there's the linked list versions. Keep going. Yeah, we got this whole idea. Look at 715. Doesn't that make me happy? Converting infix to postfix. Oh boy. Check out some of those include statements up above. Now, the big one I needed to know was it includes dstack.h. Yeah. Okay, so I come in and was input an infix expression. I see that C out. Too bad you can't turn line numbering on. And then we come down through, and remember, pushes and pops are already written for me. So inside of this code is this giant, oh, I don't know what, but you notice it shows us how to handle a left parenthesis, a right parentheses, etc. Plus, minus, times, slash, and even modulus are all going to be handled the same. When I pop, I put the number on the right. When I pop a second time, I put the number on the left. So it's one of those things that we want to be consistent even with plus and multiply like we had to be for minus and oh, you could have come up with this code, right? Maybe it would have taken a little bit of time, but this eliminates all those parentheses and gets it ready for down at the bottom. Check out the for loop at the bottom. Have you ever seen that pop remaining operators of the task? Have you ever seen a for loop that looks like that? What's the for loop doing? If I looked at for parentheses, semicolon, semicolon, what would I call that? Right now, that line is, it's an infinite loop. That bad boy for parentheses, semicolon, semicolon, parentheses is an infinite loop. How do I get out of the loop?
When you're stuck, it's empty.
When you're stuck. No, what word? There's one word in there.
Break.
Break. Break is going to break me out of the loop. I would have never taught this in the previous two courses you had. But simplicity, this is a way to get out. Technically, while a while loop should control the loop if you don't know the blah, 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 but in this case, it's okay. All right. I'm going to put you in groups. I want you to get this to work. What do I want to get to work? You can stop sharing, Jack. This nice piece of test data you have. 4, 2 plus 8, 6, 4 minus slash times should equal 24. Okay, man, what you think about that? Breakout rooms. We're going to go with 4 rooms. Let's see. I know I had Casey's audio. Casey's audio needs to go with the other Casey's. So that's going to go to room 2.
Thank you.
Yep, I have 4, 4, 3, and 3 in rooms. Any questions? All right. When you're done, we're done. I will see you Wednesday for an introduction to Qs. Instead of LIFO, it's now going to be FIFO. Okay.